Australia has just reached an important green hydrogen milestone. Plug Power has secured an order to supply a 50 MW PM electrolyzer system for Orica's Hunter Valley Hydrogen Hub in New South Wales. More importantly, the project has reached final investment decision that moves it beyond the announcement stage and into execution. The hydrogen will be used at Orica's existing ammonia manufacturing site on Kooragang Island. This gives the project something many hydrogen developments still lack: a real industrial customer, an established product, existing infrastructure, and a defined use for the hydrogen from the beginning. The global hydrogen pipeline contains thousands of project announcements, but only a much smaller number reach construction. Projects must move through several gates. They begin as announcements, then seek approvals, financing, equipment contracts, and final investment decision before construction can begin. Many proposals remain stuck at an early stage because the customer, electricity supply, permits, or financing are not strong enough. The Hunter Valley project is significant because it has moved through several of these stages. Final investment decision does not remove every risk, but it shows that the project owner has formally decided to proceed based on the available technical, financial, and commercial information. The project will be located at Kooragang Island in Newcastle, New South Wales, beside Orica's existing ammonia operations. This location gives the hydrogen hub a major advantage. It is not being developed on an isolated greenfield site with no customer or industrial infrastructure. Orica has operated at Kooragang Island for decades. The site already has manufacturing systems, experienced personnel, industrial services, and connections to the wider Newcastle port and industrial area. By placing the electrolyzer beside an existing ammonia plant, the project can send hydrogen directly into an established production process instead of transporting it over long distances or waiting for a new hydrogen market to emerge. Plug Power will supply a 50 MW proton exchange membrane, or PM, electrolyzer system. The electrolyzer will use electricity to split purified water into hydrogen and oxygen. PM technology is particularly useful in systems connected to variable renewable electricity because it can respond relatively quickly when electricity supply changes. However, the electrolyzer itself is only one part of the complete facility. The project will also require electrical conversion equipment, water treatment, cooling, compression, storage, controls, safety systems, and integration with the existing ammonia plant. Successful delivery will depend on how well Plug Power and the project team combine all of these components into one reliable industrial system. At full production, the project is expected to produce approximately 4,700 tons of renewable hydrogen every year. That is a meaningful quantity for an industrial demonstration at this scale. However, annual production will depend on factors such as electrolyzer availability, electricity supply, operating hours, and system efficiency. A 50 MW nameplate capacity does not automatically guarantee a particular hydrogen output. The project must operate consistently and maintain sufficient utilization. The annual production figure therefore represents an expected operating outcome, not simply a calculation based on installed capacity. Actual performance data will eventually show how efficiently the plant converts electricity and water into usable industrial hydrogen. The strongest feature of this project is that the hydrogen has a customer from the beginning. Orica plans to use it directly in its existing ammonia manufacturing process. That removes one of the biggest risks facing many hydrogen projects: uncertain demand. Some developers announce large production facilities before securing a serious buyer. They then spend years searching for customers willing to accept the price, volume, and delivery conditions. At Hunter Valley, the project sponsor is also the hydrogen user. Orica already consumes hydrogen indirectly through natural gas-based ammonia production. The project will substitute a portion of that fossil-based feedstock with renewable hydrogen inside an established industrial value chain. The renewable hydrogen is expected to support approximately 26,600 tons of lower carbon ammonia production each year. Ammonia is produced by combining hydrogen with nitrogen. Traditionally, most hydrogen used in ammonia production comes from natural gas, creating substantial carbon emissions. Replacing part of that fossil-derived hydrogen with renewable hydrogen can reduce the emissions intensity of the final ammonia product. It is important, however, to describe this accurately. This first phase will not convert the entire ammonia facility to renewable production. It will replace only a portion of the existing natural gas feedstock. The result is lower carbon ammonia rather than a completely fossil-free ammonia system. The ammonia produced at Kooragang Island is used to manufacture products such as ammonium nitrate. These products serve existing sectors, including mining, agriculture, and other industrial markets. This gives the project a clear downstream pathway. The hydrogen is not the final product. It becomes an input into ammonia, which then becomes an input into products that customers already purchase. This is an important bankability lesson. Investors are often more comfortable financing hydrogen projects when the hydrogen is connected to an established commodity and an existing customer base. The project is therefore not relying on the creation of an entirely new hydrogen market. It is decarbonizing a familiar industrial supply chain. Final investment decision, usually called FID, is one of the most important milestones in project development. It is the point at which the project sponsor formally decides to move forward with execution after reviewing engineering, cost, approvals, financing, and commercial arrangements. Before FID, a project may still be described as proposed, planned, or under development. After FID, procurement and construction activities can move forward with greater certainty. For Plug Power, this makes the order more credible than an early-stage memorandum of understanding. The Electrolyzer award is linked to a project whose owner has decided to proceed, although delivery and construction conditions must still be completed. Reaching FID is a major achievement, but it is not the end of the project development process. The project must now move through procurement, manufacturing, construction, installation, commissioning, and commercial operation. Each stage introduces new risks. Equipment can be delayed. Construction costs can increase. Systems may not perform exactly as expected during commissioning. Integration with the existing ammonia facility may require additional engineering. Final investment decision means the project has passed a major decision gate, but it does not guarantee that the plant will be completed on time, within budget, or at the expected performance level. The real test begins as the project moves into physical execution. Plug Power was selected because of its experience in PM electrolyzers and large-scale hydrogen systems. The company has deployed electrolyzer equipment across several regions and has been involved in industrial-scale projects in Europe and other markets. For Orica, selecting a supplier with manufacturing and commissioning experience reduces some technology and delivery risk. However, supplier selection is only the beginning. Plug must manufacture the system, deliver it to Australia, support integration, and demonstrate the required performance. For Plug Power, this project is also strategically important because it provides an opportunity to prove its technology in a large Australian industrial application connected to an existing ammonia facility. PM electrolyzers are often selected for renewable hydrogen projects because they can adjust their output relatively quickly. Solar and wind generation change throughout the day, so an electrolyzer connected to renewable power may need to increase or reduce production as electricity availability changes. PM systems can support this type of flexible operation, but flexibility alone does not guarantee low-cost hydrogen. The economics will still depend heavily on electricity prices, utilization, equipment efficiency, and maintenance. Running only when renewable electricity is available can lower emissions, but may reduce operating hours. Running more consistently can improve equipment utilization, but it requires reliable electricity sourcing and an acceptable certification structure. The Hunter Valley project is expected to use grid-connected electricity, supported by renewable energy sourcing and certification. This means the electrolyzer may draw power from the grid while using recognized certificates or guarantees to demonstrate that an equivalent amount of renewable electricity has been procured. This approach can allow the facility to operate more consistently than a system connected only to a dedicated solar or wind plant. However, grid-connected hydrogen raises important questions. The project must comply with the relevant renewable hydrogen rules, including electricity sourcing, certification, and emissions accounting. The quality of these arrangements will affect whether the hydrogen qualifies for government support and how its emissions intensity is reported. Electrolysis requires high-purity water. The project plans to use recycled water that will be treated before entering the electrolyzer. This is an important design choice because water availability and community concerns can become major issues for hydrogen projects. The electrolyzer cannot normally use untreated industrial or recycled water directly. The water must pass through treatment systems such as filtration, reverse osmosis, and polishing to remove minerals and contaminants. The project will also need to manage wastewater and treatment losses. Using recycled water can reduce pressure on freshwater supplies, but the cost, reliability, and quality of the water source must still be carefully managed throughout the plant's operating life. The project has received several layers of public support. These include 70 million Australian dollars through the Federal Hydrogen Hubs Initiative, 45 million Australian dollars through the New South Wales Hydrogen Hub Program, and up to 432 million Australian dollars through Hydrogen Head Start. These figures show that government support remains central to early commercial hydrogen projects. The support helps address high capital costs and the difference between renewable hydrogen production costs and the price the industrial customer can afford. It is important, however, not to present all of this funding as money already transferred. Different programs have different conditions, milestones, and payment structures. The largest support package, Hydrogen Head Start, is designed as production-linked assistance. The project is expected to receive support over approximately 10 years, based on eligible renewable hydrogen that is actually produced. This means a full amount is not simply provided up front as an unrestricted construction grant. The plant must reach operation, produce qualifying hydrogen, and satisfy the program's requirements. This structure gives the project long-term revenue support while also protecting public funding. Payments are connected to performance rather than announcement. For developers, this is a critical lesson. Government commitments must be examined carefully to understand when the money is paid, what conditions apply, and whether support is tied to construction, production, or verified emissions reduction. Renewable hydrogen is generally more expensive than hydrogen produced from natural gas, especially during the early years of the market. The difference between the renewable production costs and the price a customer is willing to pay is often called the green premium. Production support helps close this gap. Without support, Orica could face a higher cost for renewable hydrogen than for an existing fossil-based feedstock. Hydrogen Head Start reduces part of that difference, making the project more commercially viable. The long-term challenge is whether future projects can operate with less public support as electrolyzer costs decline, renewable electricity becomes cheaper, and industrial customers place greater value on lower-emission products. The first phase is expected to replace approximately 7.5% of the natural gas currently used as chemical feedstock at the Kooragang Island facility. This is not a complete conversion of the ammonia plant. Most of the existing process will continue to rely on conventional feedstock during the initial phase. Some observers may view 7.5% as modest, but a phased approach can reduce technical and financial risk. Orica can test how renewable hydrogen performs within the existing manufacturing system, train operators, collect operating data, and evaluate the economics before considering expansion. Gradual substitution may be more practical than attempting to eliminate all fossil feedstock in a single step. Orica estimates that the project could avoid approximately 35,000 tons of carbon dioxide equivalent emissions each year. The reduction comes mainly from replacing a portion of natural gas used in hydrogen and ammonia production. Actual emissions performance will depend on the electricity sourcing, electrolyzer efficiency, plant utilization, and the emissions accounting methodology used. The project must demonstrate that its hydrogen meets the relevant renewable or low-emission standards. This slide also highlights a broader point. Installed electrolyzer capacity alone does not measure climate impact. The real value comes from what the hydrogen replaces. In this case, it replaces fossil feedstock inside an existing emissions-intensive industrial process. The Hunter Valley project combines several features that improve bankability. It has an existing industrial site, an existing customer, an established product, government support, and final investment decision. These elements reinforce one another. The industrial site reduces infrastructure risk. The internal customer reduces offtake risk. Ammonia provides a familiar product and market. Government support narrows the cost gap. FID confirms that the sponsor is prepared to proceed. Many hydrogen projects have only one or two of these components. They may have excellent renewable resources but no buyer, or an interested buyer but no financing. Successful projects need the entire development structure to work together. Many hydrogen announcements focus on massive gigawatt-scale export projects. These projects can be attractive because they promise large production volumes, but they also require enormous capital, new ports, pipelines, renewable generation, and binding international customers. The Hunter Valley project takes a different approach. At 50 megawatts, it is still a significant industrial facility, but it is connected to an existing plant and a known customer. This makes execution more manageable. The project can demonstrate performance before scaling further. The lesson is not that every hydrogen project should remain small. It is that scale should follow market proof, infrastructure readiness, and operating evidence, not come before them. For Plug Power, this order strengthens its electrolyzer portfolio in the Asia-Pacific region. The company can point to a 50-megawatt project with an industrial owner, government support, and final investment decision that is more valuable than a large pipeline of conditional projects that may never be built. The award may also help Plug demonstrate that its PM systems can serve ammonia and heavy industry applications, not only small mobility or pilot projects. However, the commercial value of the order will depend on contract execution. Investors and customers will watch whether Plug delivers a system on time, manages costs effectively, and achieves the required operating performance during commissioning. The order is positive news for Plug Power, but it does not eliminate the company's wider financial and operational challenges. Large equipment contracts can create revenue, but they can also require significant working capital before the supplier receives full payment. Plug must control manufacturing costs, maintain the project schedule, manage logistics to Australia, and support commissioning. If costs rise faster than contract revenue, the order may contribute less margin than expected. The project therefore needs to be judged not only by its 50-megawatt headline, but by delivery quality and profitability. Winning an order is the first step. Converting that order into reliable, profitable execution is the harder test. Hydrogen developers can draw several lessons from this project. Begin with a credible customer rather than simply selecting an electrolyzer. Use existing industrial infrastructure where possible. Connect hydrogen to a real product with an established market. Develop the project in phases that match demand and financing capacity. Combine sponsor capital with grants, production support, and other funding instruments. Finally, move through real decision gates, including site control, engineering, permits, customer commitment, and financing. A bankable hydrogen project is not created by technology alone. It requires an entire commercial, technical, regulatory, and financial system that allows investors and sponsors to understand and manage the remaining risks. The Hunter Valley Hydrogen Hub has now moved from announcement toward execution, but the most important phase is still ahead. Plug Power must deliver and commission the electrolyzer. Orica must integrate the hydrogen system into an operating ammonia facility. The project must satisfy government funding conditions and demonstrate reliable renewable hydrogen production. If successful, it could become an important example of how phased hydrogen deployment can reduce emissions in existing heavy industry. If it experiences cost overruns or delays, it will also provide lessons for future projects. The central question is no longer whether the project has been announced. It is whether the partners can convert FID into operating infrastructure.